Have you ever noticed how a cup of tea stays warm far longer than you'd expect? Or how a swimming pool can feel chilly in the morning but still hold on to the day's heat hours after sunset? It almost feels like water has a memory, like it can remember the warmth or cold it once had. And yet water is just water, right? No hidden batteries, no tiny heaters inside, no magic. So why does it hold on to temperature so much better than, say, metal or wood? If you take a metal spoon and dip it into boiling water, it heats up almost instantly. But the moment you take it out, it starts cooling down right away. Water, on the other hand, is in no rush. It takes its time, slowly releasing or absorbing energy as if it's reluctant to let go. That's not just a neat little quirk. It's one of the reasons life on Earth even exists. Oceans don't just sit there looking pretty. They're giant thermal reservoirs, quietly buffering our planet from wild temperature swings. Without water's stubborn grip on heat, our world would be a place of brutal days and freezing nights, and most life as we know it wouldn't survive. But what exactly gives water this superpower? And how can a simple liquid outcompete almost everything else when it comes to holding on to warmth or cold? To answer that, we need to zoom in, way in, down to the scale where individual molecules behave like tiny, restless dancers in a never-ending crowd. Imagine you're looking down at water on the molecular level. Each molecule is shaped like a little V, two tiny hydrogen atoms clinging to a larger oxygen atom. But these molecules aren't just floating around randomly. They're constantly reaching out to their neighbors, forming and breaking connections called hydrogen bonds. Think of it like a massive, never-ending square dance where every dancer is holding hands with a few others, switching partners in milliseconds, but never letting go of the idea of connection. This dance takes energy, lots of it. To make water warmer, you're not just speeding up the movement of each dancer. You're also fighting against those bonds, pushing the partners apart so they can move more freely. That's why heating water takes so much effort compared to heating metal. Metal atoms don't have this intricate handshake network. They just jiggle faster when heated. Water's network acts like a giant energy sponge. And here's the twist. When the energy source is gone, water doesn't just drop that energy instantly. Those bonds work in reverse, holding on to that heat and releasing it slowly. The same principle applies to cooling. When water loses heat, those bonds rearrange, but they don't collapse instantly. It's like a crowd holding onto warmth in a room, releasing it bit by bit instead of opening all the windows at once. This is why an ocean can keep a coastal city mild in the winter, or why a hot bath can stay inviting for much longer than a metal tub filled with air. To really appreciate how unusual this is, we need to talk about something called specific heat capacity. That's the scientific way of saying how much energy a substance can store per unit of temperature change. And water's specific heat is enormous compared to most everyday materials. In fact, it's one of the highest of any common substance. This means that to raise the temperature of water by just 1 degree, you have to pump in a lot more energy than you would for, say, iron or sand. Here's a way to picture it. Imagine you're trying to heat up a crowd. If the crowd is made of people sitting quietly, a single spark of excitement might get them all on their feet quickly. That's like heating metal. Low specific heat, quick reaction. But if the crowd is made of passionate debaters already deep in conversation, it takes a lot more effort to get them to all cheer together. That's water. Its molecules are already busy forming and breaking hydrogen bonds, so extra energy just gets soaked up into that ongoing activity before you see much change in temperature. This also explains why beaches are cooler during the day and warmer at night compared to inland areas. The ocean absorbs huge amounts of heat under the sun without heating up quickly, then releases it slowly when the air cools. The same physics governs the climate on a planetary scale. Without water's incredible heat-holding ability, weather would swing wildly between extremes, and Earth would be a much less comfortable place to live. Now here's where the memory part becomes even more fascinating. Water doesn't just store heat, it shares it. Because liquid water is in constant motion, the energy you add in one place spreads through the whole volume surprisingly evenly. Picture pouring a little warm dye into a tank of water. In minutes, the color diffuses everywhere. Heat in water does something similar but even faster thanks to convection. Warmer water rises, cooler water sinks, and the whole thing stirs itself without you even touching it. This makes water a kind of communal bank account for thermal energy. Every molecule deposits and withdraws from the same pool, so the whole system changes temperature together. That's why when you jump into a lake, you can feel layers, warmer near the surface, colder below. But those layers are still remarkably stable compared to, say, standing in the sun where air temperatures can shift in seconds. Air just can't hold on to energy the way water can. It has a much lower specific heat, and it doesn't have the dense molecular crowd or hydrogen bonds to slow down energy loss. This is why deserts, where there's little water in the environment, have scorching days and freezing nights. No thermal memory means instant dramatic changes. On Earth, water's thermal memory works on scales far beyond your bathtub or a swimming pool. Oceans absorb summer heat and then release it months later, helping drive seasonal weather patterns and even influencing global climate systems like monsoons and El Niño. In a way, the water around us is quietly recording the story of recent weather, then retelling it to the atmosphere over time. So the next time you sip a cup of tea that's still warm long after you poured it, or step into the ocean and feel yesterday's sun still lingering beneath the waves, you'll know you're experiencing one of water's most remarkable talents. This is more than just a neat quirk. It's a fundamental reason our planet is habitable. Water's high specific heat, its dense molecular crowd, and its constant handshake network of hydrogen bonds turn it into a time capsule for energy. It doesn't just react to the present moment. It carries a memory of what happened hours, days, even months ago, and then releases that story slowly back into the world. Without that memory, Earth's climate would be wildly unstable, coastlines wouldn't be so mild, and life might never have evolved into the complexity we know. In a way, every wave, every raindrop, every lake you've ever seen is part historian, part guardian, preserving the past to protect the future. And that's the real magic. Understanding that something as simple as a glass of water holds within it the same principles that keep an entire planet alive. If you found this glimpse into the hidden life of water fascinating, imagine what else is hiding in the everyday things around you. Like this video, share it with someone who loves learning strange truths about the world, and subscribe to How It Actually Works, where we hand you the keys to unlock the science that shapes your life.